Alright, welcome everybody. Week 17, day 1. I posted a video on A-star. You see the way they're doing it is pretty similar to what I taught you all. So you have a list of, it's probably not the right data structure, but whatever. They have a list of their to-do list, which they're calling the to-search list. And they've got the process list, and then while there's stuff left in the to-do list, they grab the top element off and and they do an order in search through it to see if anybody is shorter than it. Should not, like I said, wrong data structure for the job. And then they add the current one to the process list and take it off the to-do list. And that remove is also probably going to be order in. So not. This should be a priority queue to be login instead. And then for every neighbor in current.neighbors where it's walkable and it's not processed yet, then they figure out the cost, which is the current cost plus the distance to move from a current tile to the new tile. That. And then they're going to add it to the to-do list. So that's Dijkstra. The A-star algorithm just adds the distance from the new tile to the target tile as the crow flies. Yep. That's the only difference between A-star and Dijkstra, really. It's in JavaScript or just Java. It looks like JavaScript to me. Okay. Oh, my coffee just arrived. Hang on 1 second. All right, got my coffee. Everything's good in this world. Okay. So some big topics coming up. Bridges Andrew has been moved back to Thursday for the deadline. As you guys got 2 more days to get that done. What I'm looking for, I made a new map, among other things, yesterday. Something like this. So I just made a map with a bunch of cities kind of on a diagonal like that. That'll see if your code explodes if you have a cross product of 0. So collinear points can cause problems sometimes. So just make sure it doesn't. Code's not working right, get in the habit of printing out all the things and seeing what's wrong. Alright, so you guys have any questions about the Andrew monotone chain algorithm? We're down to 8 students. Black Angels is this is an amazing album overall, by the way. Super good. Yeah, that's right. You can't remember your question. I'll pull that up over here. This is for the medium map, I believe. So I picked out several of the cities and just kind of had the cities sort of randomly connected to each other. And yeah, that's a whole. The one question you should have is for the Alaska-Hawaii map, and the reason why the Alaska-Hawaii map looks weird is because Alaska and Hawaii are not, they're in a weird place, right? So legitimately, they're in the northwest and like the southwest, but they're drawn on this map here in these spots here. So the whole is going to look really weird when you include these 2 cities, but that's not buggy. That's just where Alaska and Hawaii are. So, all right, Wallpaper Engine is updating itself. So our big topic for today is statistics. statistics is a really huge. What map do you want to include on the Canvas post? Maybe the medium one, medium.txt. That's a good one. The lines don't have to be straight. Yeah, so I actually wrote to the Bridges people asking if we can get some straight edges, but they haven't done it yet. So no, they're gonna be curved. The reason why they're curved is so you can have a line going one way and a line going back the other way, and they kind of arc so that they don't conflict with each other. All right. So, statistics. The really cool thing about statistics is that it's how we know things, really, when it comes to like science. We can know things in math by like using the powers of reason and things like that, right? Like we can add a million and a million and know that the answer is 2 million. But when it comes to science, there's a couple kind of fundamental issues with science that makes it work a little bit differently. Okay, you didn't know that you were going to be getting philosophy of science today, but you are. Because stats really ties in with it. And these issues with science are that there's always measurement error. You know, like it's maybe the measurement error is microscopic, you know, but there's always measurement error every time you measure something. You know, at a minimum, you're gonna run into the Heisenberg uncertainty, limit and things like that. There's always measurement error. There's always sort of like, you take a temperature, and the temperature is going to be plus or minus some number, right? When you do the measurement, and that's not even necessarily accurate, but it's just like 95% of the time the error is going to be between plus 0.1 Fahrenheit and minus 1 Fahrenheit, or something like that. Then you've got what you might call systemic bias, right? Like if you are trying to show that your drug is effective, you can select just the people for the control group that the drug doesn't work on, and select for the experimental people the people the drug did work on, and divvy them up after the process, and that would be like sort of a dishonest science kind of thing. And then there's also just errors in the methodology of your experiment. There's a lot of different ways that mistakes can creep into science, and the whole point of science is try to eliminate bias, to eliminate the human factor as much as possible, and to come to a conclusion like, is this the case or is this not the case? If I give you a drug, does it work? Right? And science never deals with absolutes. It's like the Jedi, right? Only Sith deal with absolutes, right? Which is an absolute statement, Obi-Wan, but we'll just not pay attention to that. The reality is science can never give you absolute truth, because there's always error and everywhere, right? The design could be an error. Your overarching theory could be an error. The measurements could be an error. People could be lying to you. You could have added the numbers wrong. There's so many different ways that error can creep in. And what we try to do is we try to do our best to eliminate and to analyze and to average and to come up with confidence levels. We talked about Bayesian reasoning last time. We want to say things to a certain degree of confidence that something's the case, right? That's science. So the standard for science depends on the field, but in a lot of fields the standard to publish is 95% confidence level. So if you are 95% confident that your drug is safe and effective or whatever, then you can publish. If you can't, then you if you're at like 94% confident. Maybe you'll publish anyway, right? Usually, though, when you're below 95%, the answer is get more data, right? So run it, you ran it on 20 people, run it on another 20, until you're confident that it works or not, right? And what's interesting is that, that there's like the placebo effect, for years I was over at a friend's house on Sunday checking out their new board game table. He's a pharmacist, and they're both pharmacists. Both he and his girlfriend are pharmacists. And he was telling a story about how there's a category of drugs that reduce cholesterol. I'm guessing maybe he was talking about statins. I'm not sure if he was. He didn't actually say which type of drugs. Statins, muscle ache. Yeah, okay. So I'm guessing he was talking about statins. I'm not sure. Don't quote me on this. But basically, there's a rare condition which statins can cause your muscles to break down, and because of that, it seemed reasonable to think that statins can cause muscle pain because it can occasionally attack your muscles. It's a very rare condition. They're very safe. Doctors prescribe statins like they prescribe potato chips, except for the opposite purpose, right? Statins like lower your blood cholesterol, basically. And so they have been warning people for years that they cause muscle pain occasionally. And sure enough, people would report they had muscle pain. And then my friend was telling me, like, they did a study, like, is this actually a real thing or not? And what they found was that if you did a double-blind study where you don't tell people if they're getting the placebo, which is a sugar pill, or a statin, basically there's no difference between the two, right? Like, some of the people, sure, taking the statins will have muscle pain, but some of the people taking the placebo will get muscle pain also. Why? Because, like, we go running and camping and get muscle pains occasionally. And if you don't set them up to expect that they're going to be getting muscle pain, then yeah. So it turns out that whole thing, maybe, assuming that he was talking about statins, I don't know. But it looks like that whole thing was just, we've been just telling people for years things that we thought we knew, that it causes muscle pain, common side effect, watch out for that. And like you saw, Harvard there had a website on it. And a double-blind study just showed, unless the study's wrong, welcome to science, it's dirty and messy, it's possible the news study is wrong too, who knows. But apparently, if you dig into it, that they don't cause muscle pain. But we've just been telling people this all along for decades. Right. So blame the lawyers. Yeah, no, it was probably just good intentions, because of this, fear of, what is it called? Is that the one I'm thinking of? Standard-induced rhabdomyolysis. Happens to 1.6 people, not 1.6, 1.6 out of 100,000 people, right? And so when you have scientific studies, right, but I thought we were learning stats. We are. I'm showing you the end goal first, right? Because most people, when they teach stats, are like, we're going to start off by averaging numbers together and, stuff like that. I'm showing you guys why stats matter so much. And they matter in a lot of areas beyond just science as well. But if you do science of any sort, you need to know stats. Okay, so here we go. Purpose: to identify case reports of stent-induced rhabdomyolysis and summarize common predisposing factors, symptoms, diagnostic findings, functional outcomes, characteristics, treatment. Method: so they search databases for case reports. One person assessed relevance. Two people independently reviewed the articles to determine inclusion in the review. Results: they found 112 papers, and majority were men, people over 45 years of age. This is the statin they used. Majority of cases reported use of concomitant conditions such as muscle pain. Look at that. Hey. Um, and so, basically, what you're going to see whenever you see an actual good scientific paper is that they're going to include the stats in it. You know, what percentage. N means the count, by the way. So N is how many incidents of that there were. So out of the 112 papers, simvastatin was the most common. So 55 of the 112 papers presumably had simvastatin in it. 64 of the 112 cases, maybe these aren't papers, they're case reports. Okay, so these are case reports, not papers. Well, I mean, it's a paper, but a paper includes one case study rather than it being like a study of like 1,000 people or something like that. So 112 individual case reports. Okay, so 64 people. So N here is the number of people, not papers. Sorry about that. So N is 64 people reported muscle pain, 65 reported weakness, 25 reported use of concomitant medications. That's the type of stem they used. Okay, so I've never seen this paper before. I've never met this man in my life. You know, I'm just looking at this for the first time, the same as you. So this is what rhabdomyolysis is common among CrossFit. Yeah, because if you over-exercise, you can actually have your muscles start breaking down. So, and then it starts dumping. So it starts dumping the breakdown into your blood, which is bad, right? It's not a. A lot of people worry about over-exercising when it's usually the opposite problem, you know. In our society, most people don't exercise enough. But yeah, among like CrossFit people, where like they're like super like hardcore aggro, you know, then yeah, you can over exercise, and that's bad. So tea-colored urine, yeah, that's a problem. Okay. CYP3A4 is a liver enzyme, by the way, that breaks down drugs. So if you're taking another drug that is also metabolized by CYP3A4, then there's less CYP3A4 to break down the statins. You'll get more in your bloodstream. So okay, so stats. Okay, the incidence is 1.6 per 100,000 person years. So what this means is that for every year you're alive, broadly speaking, and it very much depends on if you're taking statins or if you're over-exercising, things like that, but just broadly speaking, for every year you're alive, there's a 1.6 out of 100,000 chance you will get rhabdomyolysis. Okay, so that makes sense. Probability, A, you know, except it's not random, right? This is not a uniform distribution, right? It's last time we talked about conditional probability. The probability that you get rhabdomyolysis is a lot higher if you do CrossFit. You know what I mean? Okay. Statin-induced rhabdomyolysis is between 0.3 and 13.5 per million statin prescriptions. So that's actually, let's see, not too bad. Literature indicates predisposed person to statins. Okay. The percentage of Americans who take statins, including all lipid-lowering medications, are 3.4% to 15.5%. So, you know, a good 10% or so of our population is on statins and other lipid is a fat, of course, lowering medication. Okay. So anytime you have a good paper, it's going to have stats everywhere in it. like one of the key signs of like somebody trying to BS you, or pseudoscience, or just like bad science reporting in general, in which you know, the journalist is doing a terrible job, which is most of the time, unfortunately, is they cut out the actual stats, right? And let's see here, talking about how they picked out the case studies, 646, screened it down to 112. Yeah, and how you screen down these things is actually really important, which is why they're going to talk about the process they go through to screening it down, because that's a source of bias, right? Like if you just screen down people that had stat-induced rhabdomyolysis, you're going to get a higher incidence rate. You know what I mean? And so you have to be really careful, and and you have to document it, right? Like there are 608 found in the online databases. We found 38 in other databases, other sources, and then they have one researcher probably doing part of this, and another researcher, like it said earlier, doing the other part of it. So they eliminate duplicates. They did a screen down. Letters to the editor were excluded. 156 were not, you know, stand-ins or whatever. Full text articles assessed. So the 285 that passed the screen down, they assessed 116 for eligibility. So they didn't even look at all 285. You know, probably got tired. I don't know. Or maybe... Oh, no. Records screened. So of the 116, 22 of them... 22 of them... Let's see. 116, yeah. 22 of them were excluded, and 94 of them were included in the study. And then they're going to probably talk about why they did that somewhere. Data extraction, study selection. Whose case included eligible for inclusion if reported a definitive diagnosis of stent-induced rhabdomyolysis through lab evidence of muscle breakdown toxicity. Yeah, and that's what my friend was talking about. Like they ran these studies, and they found like people would report muscle pain due to statins, even though they didn't show any blood evidence their muscles were breaking down. You know, and that's presumably what people thought the muscle ache was due to, right? Was like, maybe you don't have rhabdomyolysis, maybe it's breaking down your muscles a little bit and it kind of hurts and things like that. And so they did blood work on the people and found it was just all up in your head. Yeah, it's interesting. So I hope this is interesting to you guys too, by the way. It's interesting to me. I just read about this on Sunday. And then look, stats and, you know, numbers in how many males you have, how many females you have, right? You know, you got all this data here. And flaccidity, tenderness, nausea, shortness of breath, malaise, fatigue, dark urine, muscle pain. Look at that, muscle pain, muscle weakness. Mortality rate of 15%. Older people died more often. 15 of the 17 fatal cases were men at a mean age of 65 years. Okay. Alright, so they're looking at the people that have stent-induced rhabdomyolysis, age breakdown, male-female breakdown, pre-existing diseases. Okay. So what they're going to do... okay, here we go. Standard deviation of 7. Stats, again. So what a standard deviation is the sort of... You can think of it as like the width of the bell curve. So if you have a standard deviation of 1, then 68% of the area is within 1 standard deviation of the mean. The mean is the average, the center point here. The expected value, right, is the mean, the highest point. And then 68% of whatever results you are going to get are within 1 standard deviation of the mean. And then if you go out 2 standard deviations, it goes out to 95%. If you got 3 standard deviations, it covers 99.7%. And so if you've ever heard people talk about like 5 sigma reliability and things like that, this is the lowercase sigma, right? I think. Right. If not, we'll remove it in post. Okay. 6 sigma reliability. So that means that their process is reliable out to 99.99999, yeah, whatever, 99.99966%. Okay. So it's designed to have production and reliability testing and things like that, so that your stuff is highly reliable and you can get certified in the thing. So typically speaking, for confidence testing, we use 95%. So if we're 95% confident that something's the case, then we publish it. Some disciplines use higher degrees of confidence, like 99%, 99.99966%. Okay. It depends on the field. Particle physics typically has much higher standards of evidence required, because you can always just shoot another electron at something. You know what I mean? So like when they were announcing the Higgs boson had been discovered a few years ago, they just kept running experiments, right? Like you can just keep colliding things together over at the Large Hadron Collider in CERN, the border of France and Switzerland. You just keep running the experiment, and as you gather more information, your confidence goes up, assuming you're getting positive results, and eventually it crosses the 5 sigma, the 6 sigma threshold, whatever, and you can publish, right? Whereas for things like this, where you've got, sometimes you just have a couple dozen people, you don't expect the significance to be as high. So what we have here is standard deviation of 6. So mean time to onset was 9 days, and you might think of this as like plus or minus 6, and that covers 68% of the cases, right? So between 3 and 15 days covers 68% of all the cases. That's why they publish the standard deviation there. So you get an idea of how much variance there is in the data, how wide that data is. Is it always on day 9? And we want to know things like that, like for COVID, right? How long, if you get exposed to COVID, on average, how long does it take for symptoms to appear? And what's the variance? What's the variance in that? Plus or minus 2 days? Whatever. Mean hospital length was 11 days, 11 and a half days, plus or minus 7, right? So that means 68% of cases will present at the hospital in 4 days to 18 days. Okay. And so this is a literature review, so they're not going to be doing statistical testing, but I think you can see that numbers are like really important to science. Okay. And things like what we're going to talk about today are used like just all throughout science, and that's usually a good sign that what you're looking at is in fact scientific. So with that in mind, let's do this. Let's start off with the most boring part of stats, which is like middle school statistics, but it's important nonetheless. So let's say you got some numbers. Let's say that you're giving a drug to somebody. You've got this pill here. It's a magical pill with magical colors. Look at that. Contains the galaxy in it. Okay. You're giving this magic pill to people. And you give... Yeah. So the magical pill gets given to what's called the experimental group. And then you've got a completely boring sugar pill here called the placebo. And the placebo is given to what's called the control group. Right. And they're not told which group they're in. If you're doing a double-blind study, not even the people giving the medicine know which one is which. They're just handed a pill. The pills look the same. They don't actually contain the galaxy colors within them. And the researcher will give a pill and a pill. And they don't know which group they're in. And the researcher, or a friend of mine actually does drug trials. And if it's double-blind, he doesn't know either. But either way, the people then have to sit in his office for a while, and he has to observe them. And if they have a serious reaction to the drug, then he's got to be on hand to counter it. He's got his doctorate in pharmacy. So, space pill gateway to the cosmos. Nice. Okay, so let's say you do this and you give it to five. There's 5 people in the experimental group. Whatever. I don't need space colors for this. So 5 people in the experimental group and 5 people in the control group. Okay, not a large study. Okay, and of the people that you give it to in the experimental group, they grow on average. One of them grows 5 inches taller. One of them grows 1 inch taller. One of them loses an inch. One of them nothing happens, and the other one nothing happens. And then for the experimental group, or for the control group, one of them grows an inch, 2 of them lose an inch, one of them grows 2 inches, one of them doesn't change. And so the question is, did your drug do something? Now you might be like, well, 5 inches in a week or whatever it is, that's, I'm kind of making up an example here. Nobody grows 5 inches in a week, but this could be like your LDL level for cholesterol. It could be the amount of pain you experience on the pain scale. It could be a lot of things. The point is, doesn't number, but just for the sake of amusement, let's say that the first person to give the space pill to grows 5 inches taller in a week. There you go. And so you might suspect, there might be something going on here. Maybe this experimental drug works, or at least it works part of the time. 20% of the time it works 100% of the time. I don't know. But you can't just say, okay, it works because one of my people got taller. It's possible this was a measurement error, right? They could have been slouching or something. Who knows, right? And so what you have to do is you have to do stats. You have to do stats to figure out, did the drug work? And if it did work, how confident are we that the drug works? Okay. So the first things we do when we do stats is we do the mean, the median, and the mode. And we're going to be doing this for the experimental group and for the control group. Okay. So the mean, yeah, exactly. The mean is the average, the expected value. So what was the expected value of this? How much on average did the experimental group go up in size? Wait a minute. On average, how much did the experimental group change? And also we got the count. All right, we should probably write that down too. It's 5 for both of these. On average 1, right? Plus 1, minus 1, 0, 0, and 5 adds together to be 5. 5 divided by 5 is 1. Yep. So on average, the experimental group grew 1 inch in a week. Okay. So mean is the expected value or the average. And so to do an average, you add together all the things and divide by the count. You guys should know that by now, right? So to do an average, you add together all the elements and then divide by the count. Okay, what about for the control group? Minus 1, plus 2, plus 1. 1 divided by 5 is 0.2. Sure. The control group also grew. Oh, that's interesting. But I thought it didn't do anything. Yeah, Remember, there's measurement error, right? There's measurement error. When somebody comes in, they could be sitting up tall. Like, my spine isn't changing in height right now, right? I'm just changing my posture. You know, that's easily 2 inches of, you know, difference. Just, is a study double blind? Yeah, it's a double blind study. So the people taking it don't know which drug they're getting. Is it the real one or the control? And the people giving the drug, the people administering the drug, don't know either. So somewhere somebody's recorded down which pills are which, so that you can get your right data. But this is a double-blind study. It's the a double-blind randomized experimental control study is like the gold standard in science. And you don't always get the option of doing this, right? Like, sometimes it's impossible to do a double-blind study. For example, if you're studying teaching methods, you know, what if the teaching method is to teach students in a pitch black classroom, right? You can't hide that from the people, you know what I mean? Like, the people in the classroom know that it's black. Like, you turned off all the lights, you put the blinds down, all you have is the overhead projector. You can't, it's impossible to do that in a double blind fashion. So there's different kind of standards of like reliability and stuff like that. And the reason why it's less reliable is like there's something called the Hawthorne Effect. And so the Hawthorne Effect was when they were looking at, like, I think it was like a factory of some sort, and turned out official. They experienced a series of lighting changes in which productivity was said to increase with almost any change in the lighting. It turned out not to be true, and it said it works for sure, methodologically poor. Yeah. Anyway, so the way the story goes, at least, is that they want to see what happens if we increase the brightness in the factory, and the productivity went up. They increased the brightness and more productivity went up. Then they decreased the brightness, and productivity went up. Like, wait a second, they decreased the productivity, the decreased lightness, and productivity went up. And so the Hawthorne Effect is like, when you know that you're being experimented on, then people will respond to it, right? Like, if I told all of you guys that researchers from the National Institute of Computer Science were going to be watching the Discord chat today, you know, and seeing how often you guys participate in chat, that affects your chat. You know, you're not going to be posting Anchorman memes, you know, and things like that, right? You know what I mean? Or maybe you would, I don't know, right? But it'll affect you, right? And so you don't always have the ability to do a double blind study. Okay, but it's the gold standard for a reason. Okay, so the median is the middle value. So the mean is the average. If we want to look for a human description here, this is the average. The median is the middle value. So you sort and take vector dot at vector dot size divided by 2. That's how you do the median. Pretty easy. Sort it, take the middle value. If you have 2 middle values because you have an odd number, then or no, you have an even number, then you average the 2 middle ones. If it matters. If you have millions of values, it doesn't matter. So, you know, if I had 1,000,001, I probably wouldn't even bother averaging the 2 together. Or maybe it would. I don't know. It depends how rigorous I want to be. But median is oftentimes better than averages, and that never made sense to me as a kid. By the way, why median is better than an average? Because here you can see if we take the median value here is if we sort this, we have 0, 0, -1, 0, 0, 1, 5, and so the median value here is 0, right? And as you know, kid me is like, well, that's not good, right? Like, you know, clearly one person grew significantly. Like, shouldn't we be like trying to focus on that guy and figure out, you know, what happened to him? But that's the whole point of a median. The whole point of the median is to throw away the most extreme data, right? And to take the most boring data. The median is the average person, not the average result. It's the result of the average person. You guys, does that make sense to you? So if you're looking at household income in America, if you're looking at how much people make in America, the presence of like your Bezoses and your Gateses and things like that will throw off the average. If I were to bring Bill Gates into our classroom here, the average income of people on Discord would skyrocket. Presumably, you don't make more money than Bill Gates. So that doesn't help though. If I say on average you guys make $1 million a year or something, like cool, you know. And so the median value is the amount of money the average person on Discord makes, which would be, I don't know how much students make, not very much money. At least when I was a student, it's quite poor. So the whole point of a median is to ask what is the experience of the average person, right? Because it's utterly unhelpful to say, well, the average income's $1 billion, or, you know, when you've got a Bezos or something and they're putting their stepping on the scale, you know, that heavily. So and once I understood that, then I understood why people care about the median so much. Because as a kid, I never really understood like why you'd even care about it, you know, because the average always seemed to me to be better. So median income in California is $80,000 a year. Median income in Mississippi is $45,000 a year. So this is the income the average person makes in each state. This is not average income. This is median income. 83,000 in Hawaii. Wow, Hawaiians make more money. The average Hawaiian makes more money than the average Californian. What about New York? 72. Massachusetts 85. Maryland 86. Wow. New Jersey 85. Maine 58. Wow. South Carolina 56. Okay. Is this household or is it? Income inequality in the U.S. is considerable. Median wealth. Another inequality stamp, the median wealth per adult. Okay, so this is per adult, not household income. It's per adult income, which is not the same thing. So if you have two working incomes, household income, that gets added together, right? In the highest ranking country, it's $146,000 a year. Yeah. So one of the reasons to look at median income is because that kind of does away with the outlier effects of having lots of money in a few people's hands. So 60,000. So you can see there's a pretty, I guess the highest is going to be Maryland, I guess. 86, and then Mississippi's at 45. I wonder if it's poorer. Yeah. So I guess Mississippi's the lowest and Maryland's the highest, right? Okay. So that's the median value. All right, what's the median value for control? One of the corporate tax shelter states. It's also got a lot of government people in it, and the government's a giant cash cow. You don't have to compete for your money; you just tax people. There's also some good colleges there. I worked with the University of Maryland at College Park for a while. Also, it's Baltimore. Yeah, I mean, Baltimore is not, that nice a city, to be honest. At least the last time I was there were definitely parts of it you didn't want to end up in. DC as well, for that matter. So what's the median income for the control group? friend of mine who lives there was out drinking. Somehow ended up in a neighborhood he shouldn't be in, and just kind of walking around drunk, and one of the people in the neighborhood came up. He's like, "Buddy, you shouldn't be here right now." He's like, "Why not?" He's like, "Just not the right neighborhood for you. Let me call you a taxi." And the guy calls a taxi and sticks him in the taxi and sends him home. It's in The Wire, based in Baltimore. Never seen The Wire. I heard it was good though. So what's the median? Sort and take the middle element. What's the median? 0. Forget. So if we're looking at the average outcome, the outcome of the average person, it's the same between the two, right? So yeah, 0 in the middle, -1, -1, +1, and 2. And there we go. So yeah, the middle element is 0. Okay. And then the mode is the most common outcome. So most common So which result happens the most often? And so you do that by doing a histogram. Okay. So do you guys remember how to histogram values in C++? Like counting how often each of these scores comes up? So for this one, yeah, you're right, Sarah. The mode is 0. So 0 was the most common outcome. What about for the control group? Which one of these outcomes was the most common for the control group? -1. Okay. So these are your basic stats, and let's go ahead and maybe let's see. I got a worksheet for you on this. Maybe just run through some basic stats here. There we go. Yeah, so worksheet 9. I'm going to go ahead and pause the recording and just... Oh, standard deviation. Right, so standard deviation is calculated by taking these numbers and putting them into a standard deviation calculator. The actual way of doing it is you figure out the mean, and then you go through and you difference the individual values from the mean. That's a pain in the ass to do by hand. So the way I do it is I'm like, bloop, copy, go into a standard deviation calculator, paste, and then figure out the standard deviation. So the standard deviation is, again, 68% of the points will be within one standard deviation of the mean. Okay. So, so do 13 to 20. Okay. And I'm going to give you guys, we'll include the break in it. So we'll come back at 11:30. Does that sound good? So I'm estimating this will take you about 20 minutes to do. And, no, that's a little bit too much time, huh? 15-minute break. No, 11:13. Yeah, let's say 11:30. Okay, that'll give you plenty of time to work on this. And then I can give you more problems to work on if you guys. No, is that too much time? Will this take you 20 minutes to do? What do you think? Not sure. And you can eyeball the mode, right? Like, you can see which one happens the most often. This isn't sorted, so this one's a little bit more annoying. But one of the numbers definitely comes up more often than the other ones. So, okay. So let's come back at 11:30. And then we'll finish off by doing p-value testing. T-tests, stuff like that. Okay. So this is on Canvas. This is worksheet 9. If you want a copy of it, so you don't have to just stare at my screen. Okay. So I'll just put up on chat. I'll just stop the recording here. I'll put up on chat questions 13 to 20 on worksheet 9. Okay. Come back at 11:30. All right. See you then. All right, it's now 11:30. Let's keep going. So the mean, the median, the mode. I just whipped up a little program real fast over here. So let's run it. Please enter an integer. 3, 1, 4, 5, 7, 3, 2, 1, 8, 10, 30, 2, 3, 6, 42, and 3. The average is 8, and the mean is 3. Okay. Not the mean. Did I say the mean? Median. All right, sorry, median is 3. Okay, so the mode, though, we need to calculate. This code should be pretty straightforward to all of you guys. Make an empty vector. While true, we read an integer. If they type in 0, we break. We add it to the vector. And if the vector is empty, we return 0. We do that to avoid division by 0 errors. Anytime you do a division, your first thought should be stop a division by 0, right? So always make sure that number is going to be fine. And also it stops this from going out of bounds as well, because we know there's at least one element in it. So anytime you do a dot at with a element to the right or an element to the left, make sure you're not going to go out of bounds. And so by making sure that we have at least one element, that will prevent that from killing our program. So we start off by just dumping the vector to the screen. So for every element in the vector, we print it. So we print out by just dumping the vector. We then use a range-based for loop to add all the elements together. Pretty easy, straightforward stuff. If any of you don't know what's going on here, just ask. The average is going to be the sum divided by the size. That's your standard average formula, right? Pretty easy stuff. We could use a double if we wanted. We could cast this to a double and get a it's probably even easier to do it this way. And 1, 2, 3, 4, 5, 5, 5, 5. Yeah, and get a decimal out of it if we wanted. Okay. And so for the median, if we want to do a same thing, we can divide by a double here. 1, 2, 3, 4, 5, 5, 5, 5, and get decimals if we wanted. It just depends what you want. But the question is, how do you do histogramming, right? And so for histogram, you want to count how many times each number appears. And the easiest way of doing that is with an unordered map, right? So an unordered map connects one thing to another thing. So in this case, we're going to count how many times each integer appears. So if the number 42 keeps coming up over again, unordered map between an int and an int called map. I don't have any good names here. So what we're going to do is, actually we just do it while we process the thing. And technically, we could probably compute the average while we're reading the number. We don't actually have to put it into an array, but or a vector, but it's easy to do that way. So when we're reading it, we're not only going to push into the vector, we're also going to add it to the map. So we're going to say map x plus plus. There you go. What do you guys think? Seemed a lot harder, right, when you had to write it. Computing the mode, which one is the most common. Sort it. Go through. Find. Okay, this guy's 5 times in a row. Okay, he's the biggest. Okay, this guy's happened 6 times in a row. Nah, I don't have to do any of that. Just histogram it. Okay. And then we can just copy the results into a vector, or we can just do a for loop here. Okay. So int maximum value -1 or 0, whatever, and max count equals 0. Okay. So for every entry in the hash table, this is a pair. So hash tables, when you do when you have an unordered map and you do a range trace for loop over them, returns pairs, returns the key and the value. For every element in the hash table, returns the key, returns the value. And so what we're going to do is get for every key value pair in the map, if the dot first is the key, the dot second is the value. I guess we just make it max, name it this way. So if, let's just do it this way. Int key equals x dot first, int value equals x dot second. So what we're doing here is we're just splitting this pair up into its components and giving them human readable names. So for every key and value in the hash table, if the value, which is the count, if the value is greater than max value, we've now found the biggest person so far. And then we will say the biggest person we found is that key, and the biggest count is equal to the value. Okay. See if it works. 1, 2, 3, 4, 5, 5, 5, 5, 5, 5, 6, 1, 0. So the mode is 5. Most common element. Do you guys understand how this works here? By the way, in general, you shouldn't use square brackets with unordered maps. In this case, it does exactly what we want, though. So we try accessing, like if we enter the number 900, it goes to spot 900 in the hash table. Doesn't exist. The killer thing about square brackets is that it inserts something into the hash table if it doesn't exist. So if you were trying to read from a hash table using square brackets and it doesn't exist, it will insert and default construct something out of that spot. So what happens is we try reading from that spot, it doesn't exist, it goes in at 0, it then increments up to 1. Square bracket places it if it doesn't find the key exactly. So it actually does exactly what we want in this case. And so the better way of doing this would be, in this circumstance it's fine. But in most circumstances what you want to do is say if map.contains x. So if it's in the hash table already, then map x plus plus is probably the easiest way of doing it. So basically, in this case it works because 0 happens to be the correct default value, so everything kind of works out. But in general, you should use .contains or .count if you're not using C++20. And so in general, when you use square brackets, you shouldn't use it unless you know that it's in the hash table already. Okay. But in this case, it does exactly what we want. So this counts how many times each word appears. So every time you type in a 900, it goes to slot 900 in the hash table, wherever that hash is to, and increments the count in there. So do you guys get that mapping between the number, if I type in 4200, then the value associated with it by default is 0, and then we increment it every time 4200 comes up, it increments the count by 1, and then at the end here we just go through all the keys and values and find the one whose value is the greatest. What if the set of values that we have has a 0 in it? It won't work. This code won't work because I use 0 to indicate done. Right? It doesn't matter for the histogram here. For the histogram, it doesn't make the slightest difference in the world. And so you would just need some other way of indicating that you're done. And so you could do something like if not cn break, something like that. This is going to be a little bit harder to get out of, right? 1, 2, 3, 4, 0, 0, 0. So how do you break cn? How do you indicate there's no more data to be read? Anyone know? Because there's no number now. Squirrel. Nope, not with readlib. Readlib fixes it. Hit enter. Nope. There is no way out. Unless you hit Control D. Control D is end of file. And so if you hit Control D stands for end of file, obviously. Not Control C. Control C kills the program. Control D, it's like the file was closed. And this is actually a fairly common thing. If you like, what if you just type cat, right? 1, 2, 3, 4, 5. It just echoes things to the screen. It runs forever. You have to hit Control D to get out of it. Control D is the end of file character. Cat by default assumes you're reading from a file. So there is no escape from cat. Okay? So when you learn Unix, Control D is like more, you know. Less. Yeah, okay, these only work with files. Standard input, there we go. All right, Control D will get you out of it, presumably. Okay. Yeah, but then the rest of your code doesn't run, right? So I typically don't do that with students because students don't know about Control D, and so they're like, I'm done, let me out of here. All right, so Control D exits, or it sends an into file, then cn becomes invalid, you can't read from it after it's been closed, and then you can do your average, your median, and your mode. So 234 happened the most. Okay. You guys down with that? Control, if I can type. Control D to quit. Okay. You're down. You're totally down. Okay, cool. So that's yeah. The mode's probably the most annoying part of it to do. Some people do it by sorting, and then as you go through the sorted array, you are like, oh, this is a new number. You start counting how many times that number appears, because it's already sorted, right? Because for the median calculation. And then you're like, oh, this is a new number. Okay, well, the last number we had 5 of. Oh, that was more times than the previous one. And the logic gets kind of annoying on it. So I would just use a hash table. Hash tables are fast. You know, nothing wrong with it. Running time's actually probably not going to be as good because you're inserting into a whole nother data structure. I don't know if it'd be noticeably different, but it probably would be slower doing it this way than just counting. But it's a lot faster to write, and there's a certain virtue to just having code that's easy to read and easy to write. Unfortunately, max element doesn't work in hash tables, I don't think. There's a max element function. Let's see if that works. Map.begin, map.end. All right, maybe it does work. All right, let's find out. See how. You don't like that? Oh, it's a pair. All right. Doesn't like that. Oh, it's in. They returned 1. So, I guess not. I don't know. Oh, it's probably sorting on the key, maybe. Let's see. What is that returning? Or if it's finding like the biggest key. Okay. 1, 2, 3, 4, 5, 5, 5, 5, 5, 6, 7, 8, 9, 9. Control D. Yeah. So it is finding the maximum key, and the maximum key has a value of 2, which is not what we want. So, yeah, I'm curious if there's something in the unordered map. Max value. I don't want max key, I want max value. Max key, no, not you. That's easy. Max size, max load factor. Sometimes when people implement these things, they have a an iterator that points at just the values, and you can call max element on that. I'll have to look at that more, but either way, this approach works. Where basically I'm just looping through every key value pair in the map, and if the value is bigger than the max value we've seen, then we write down the key and we write down the value. So, yeah, unfortunately, max element doesn't work. So, okay. Cool stuff. Good programming. Good times. All right, let's move on. So, dead silence on Discord. So, okay, let's do this. So, let's get to the meat of this assignment, which is of the lecture today. So, given this data, what's our standard deviation to? Should probably punch that in. Standard deviation calculator. Punch in some numbers. 5, 1, 1, 1, 0, 0. Standard deviation is 1.85. Need to add an entry for that. Standard deviation, which is lowercase sigma, is 1.85. And then for the control group, -1, -1, -1, 2, 0. Standard deviation for this one is 1.17. Okay. So the question is does the experimental drug do something? Right? This is the big question in science. Did it do something? Kind of looks like it did, because one of the people grew 5 inches in a week. Although they could have been just slouching extra much. Like, who knows? Right? How do we tell? Did it work? This is the big question. Did it work? So how do we know? And with what confidence do we know that it worked? Okay? So what you can do is something called a statistical test. And there's a lot of ways of doing statistical testing. But the one we're going to go over today is called Student's T-Test. And what you'll see is a pair of Gaussians like this. Good. And what you'll see is you have your pre-treatment blood pressure, which is a Gaussian. Obviously, in real life, you don't get nice, perfect bell curves like this. Instead, you get things that look kind of like that instead. So you have the people come in. You give them blood pressure medication, you measure their blood pressure after it takes effect. You can see that the mean has dropped from 145 to 138, it looks like. But we don't know if this was significant or not, right? How many people do they have? 175 at the top level. They actually haven't broken this into bar charts. We actually don't know the count. And so we can't actually determine if this is significant or not without knowing the count, right? We know it's at least 175, if that's the up here, but without the bar charts, we don't know actually how many they had. So, so what you have with a t-test is you have the average, and then you have the standard deviation, right? Which is represented by this error plot here. And you say, all right, well, is there a statistically significant difference in this case between men and women as far as body weight comes? And that's probably kilograms, right? So that's 63 kilograms on average for a female and 88 for a male. So is it a significant difference? What do you guys think? Just eyeballing it. Do you think that you could, if I were to give you a random point, would you be able to classify it as likely male, likely female, given the stats? Are these populations distinct? They are. Yeah, pretty obviously, right? Like there's not a single female heavier than a male, which is obviously not representative of real life, but in this study, all of the women are lighter than men, which makes it a very easy test, right? Your classifier is quite simple. If the body weight is below 72, it's a woman. If it's over 72 kilos, it's a male. It's, like I said, it's not very generalizable to the general population. But for these people, like let's say that you're writing software for some security system, the person walks up and they stand on a weight measuring plate or something, then they swipe their ID and it says it's some woman, and you're like, oh no, you're too heavy, it's not, can't be you, right? So in this case, yeah, it's quite a distinct population. And in fact, what you see here is the p-value. So you'll see this all over the place in scientific papers. And that's why I was saying with that Stanton paper that I was showing earlier, I didn't have it because they weren't doing statistical testing, right? They were just reviewing case studies and things like that. But anytime you're doing statistical testing like this, like did the drug work, what you want to know is how confident are you that your drug did something? And like I said, usually the cutoff is 5%. So if there's a 5% chance that it's due to chance, that's the threshold for publication. So what we have here is a p-value of less than 0.0001. So what this is saying is that there's less than a 0.0001, so that's a 0.01% chance that these groups are distinct just due to chance. So this is a highly significant finding. N is 40, and the difference in means is 20.1 kilos. Yeah. And you would also need the standard deviation in here, which is this amount, which would be an eyeball at around, 4 or so. And this p-value here tells you how significant the finding is. Another way of thinking of it is, what are the odds that you just got lucky? There's a lot of different ways you can kind of think about that p-value. But what you're looking for is a p-value of less than 0.05. 0.05, not 0.0001. This is a very significant finding. 0.05. And what 0.05 means is that you're 95% confident that it's an actual finding and not random chance, right? So, right. So basically, you've got what you're looking for is the odds that you just got lucky are less than 0.05. That's what the p-value means. And different publications have different thresholds for publication. Like I said, in particle physics, it's like way out here. They're looking for like 5 sigmas of significance. Maybe in psychology and less rigorous fields, it might be a p-value of 0.1 or less. Like I said, sometimes 0.06 is still enough for publication, especially for like preliminary findings or like if you have a low N, then the lower your sample size, the less significant it is, right? You need to get more people into the study to find out if it's significant or not. Okay, so if the two groups differ, who knows p-values? Who can explain p-values? That's funny. Yeah, it's actually quite controversial what it actually means. So that's why I said there's several different ways you can describe this. But basically, like let's say that there was no effect, right? That this drug of ours is completely a placebo, right? What are the odds that because it's random, right? It's a random process. And so what are the odds we just happen to get a difference of this much, right? What are the odds the blood pressure in this population would drop from 145 to 138? And that's what the t-test does. Okay. So the t-test is difference in means divided by standard variance divided by the count. So basically what you do is you go to an online calculator and you plug in the mean, the standard deviation, and the count for each of the two groups. And then you don't have to look it up yourself, right? T-test calculator. So you don't have to do all the math yourself because we're living in a world with computers. Make use of them. Data entry, unpaired t-test, standard. Okay, there we go. So you enter the mean, the mean, standard deviation, and the count. Okay. So once you're kind of familiar with the vocabulary, then all this stuff is actually pretty easy to do. So we've got our magical, mystical drug and a control, and we want to know, did it work? All right. So let's find out. Did it work? So mean for group 1 was 1, let's say. And for group 2, the mean was 0. No, so the mean was 0.02. Standard deviation for group 1 was 1.85. So that's how wide the Gaussian is, right? It's the width of the middle 68% of a Gaussian is the standard deviation. So 68% of all numbers would fall within between 2.85 and negative 0.85, right? So that if the mean is at 1, then you go out to the right 1.85, you go to the left 1.85, and you would expect 68% of your values to fall in that range. And the mean for this one is 1.17. And the count was, 5 for each one. Calculate now. Let's find out if it was significant. And it's not. Unlucky. So our p-value is 0.4. So there is a 43% chance that our results here were due to chance. Okay? Make sense? Can't publish. Sorry. Dang. All right. Sucks to be you. Get more data. Do you guys understand? Because at first glance, it looks like our galaxy drug did something, right? Because look at that, 5 inches in a week. It's incredible. Let's exclude the bad data. Well, if you exclude the bad data, if you exclude the outliers, then you got nothing, right? They're going to be almost identical. But the reason why we do these tests is because the world is a noisy, messy process, and there's just noise and data and experimental error and all this kind of stuff. You want to know, like, did it actually do something or not? And if, and this was like, a 57% chance it did something. But 57% chance that it did something does not meet publication standards usually in most papers, right? It might be enough, like, you could present this to your, like, dean of the college, be like, hey, I want to run this on more people, because we got this guy right here grew 5 inches in a week. So It might be enough to get your local institution to like run more trials. But it also doesn't mean nothing happened either. It just means it's not significant. So, statistical polling in politics. Yeah, so, well, there's two issues with that. First is who's answering the poll. Right? Because like I said, there's a lot of different ways that bias can come in. And so if you're doing a phone survey of people, who has a landline these days, right? If you're only calling people with landlines, you're not doing a representative sample of the entire population, because most people don't have landlines these days, right? I remember when it was weird to only have a cell phone and not have a landline. And nowadays it's the opposite, where it's kind of weird to have a landline, right? So if your phone survey of politics is only people with landlines and you're calling during business hours, then you're not going to be getting people who work, right? And if you're getting people with landlines only, you're probably going to be getting just old people, right? So you're going to be surveying old people. And you might not even realize this, right? You might just be like, hey, I'm just calling everyone's landline number. You know, it's representative, right? And you don't even realize that what you're going to be doing is getting a whole bunch of people that are retired. And that is not a representative population, because the different age brackets vote for the political parties differently, right? So old people do vote. Yeah, I got nothing better to do, I guess. No, I'm kidding. But they vote differently, right? Because they have different interests and different backgrounds and things like that, right? So as far as politics goes, like a lot of old people like voting for Democrats because they try to increase Medicare and Social Security and things like that, whereas Republicans have a reputation, whether deserved or not, of trying to vote against more benefits to old people. But Republicans try to get the old person vote by doing things like allowing you to invest your Social Security in the stock market rather than keeping it in Treasury bonds, which is what Social Security is normally invested in. And Treasury bonds are at like 0% or something like that. I haven't checked recently, so who knows. 13 week is going to give you like somewhere around 0%. Okay. Yeah. So they 30 years at 2%. Yeah. So Treasury rates, short-term Treasury rates are very close to 0, and then we go out to the longer one. You're talking about 1% or 2% on your money. It's a really small, interest rate, and so stock market. Let's see, Vanguard. Yeah, whereas the 10-year rate on, if you just invest broadly in the stock market, you're just like, I'm going to just invest in the Standard & Poor's 500, right? And so Vanguard makes these vehicles where you invest literally in the entire stock market, of whatever stock market of your choice. In this case, it's the S&P 500. And so you can see it goes up, it goes down, but the 10-year performance on it is massively bigger than, here's the 80s. So if you bought a 30-year, that'd be, what would it be, 91, 35, and it's now at 101. So it's tripled, despite being down quite a bit from the internet bubble days. Oh no, that's 2001. Sorry. Where's year to date? Sorry. Yeah, no, it's at 430 now. Why is max not? Oh, it has to scroll. Okay, there we go. All right. Sorry. Yeah, the 30-year performance then is over 15 times Right? Whereas the treasuries give you 2% annually. So, stock market carries a higher risk. Yeah, it does. And so that's why Democrats are opposed to it, because they don't want, like, if the stock market crashed and old people lost their retirement, then the government would have to bail them out so they don't starve, right? But at the same time, it's like putting everyone's retirement into something that essentially gets no interest is because inflation is higher than zero. Like you're actually losing money if you're invested in short-term treasuries right now, right? So politics is complicated, but the point is, if all you're doing is serving old people, then you're not getting a representative population. See, so that's what I'm trying to get at. Like when you do science, like there's a lot of sources of like bias and like ways that like you can make mistakes. There's type 1 errors and type 2 errors and all this kind of stuff. But at the end of the day, what you're trying to do is determine, did it work? I'm putting fertilizer on some crops. Did it work? And you can't ever say like absolutely yes it did or no it didn't, because science doesn't work that way. Science does not deal in absolutes. Science deals with confidence levels. And so in science, if we say did it work, we're saying yeah, with a 95% confidence we can be confident this fertilizer works. But we don't use all those words. We typically say yeah, this fertilizer works. Yeah, but in science, remember, that's not an absolute truth. It's just like, yeah, we've done a study, and we did a double-blind study where we put the fertilizer in a control, and the fertilizer crops grew higher, and we did enough that it's 95% confident it works. We typically don't use all of those words when we're talking casually, but in a paper, yeah. If you're reading a news story, yeah, that's exactly what we're looking for. Like if I want to know if a fertilizer works, sure, casually, the person at the garden center could be like, yeah, sure, it works great. But if I'm looking at it from a scientific lens, I'm like, all right, what's the effect size? How much did it work? Right? In this case, the effect size is 0.8. You guys see that? So the effect size of our drug here is 0.8. People got, on average, 0.8 inches taller using the Galaxy drug than the placebo. That's the effect size, 0.8. What's the effect size? What's the standard deviation? So the effect size was 0.8. The standard deviation was 1.8, which is not a good sign, right? Because it's within that, margin of error, really. And what's the N? How big is your study? 10 people. Okay. All right. A lot of gray areas, yeah. That's what I'm trying to say. Like in science, it's very rare to know something like particle physics, maybe, right? With particle physics, you can run trials millions and millions of times. And at a certain point, you're just like, I'm 99.99999 confident that the electron weighs this much within this very small margin of error, right? That doesn't eliminate like methodological errors and things like that. But, as far as like measurement errors goes, you can be pretty certain. But for things like this, where you've got people and you have to bring them into a trial, let's say that we did this with 100 people instead of 10, right? Well, now it's a significant finding. See that? The p-value went from a 43% chance that it was chance to a 1% chance that it was chance. That's why, our default answer to like, did it work, is if you get an ambiguous finding, as you say, well, run more tests, right? You don't say no, it didn't work. When you have something like this, whenever you get a no, did it work? No. Well, get more data. Right now you only have 10, and so either make the trial bigger or give up. It's hard to say when something doesn't work because the effect size might just be small, right? Like what if there was a drug that I could give to you that would increase your height by a 32nd of an inch? 100% of the time, guaranteed. Tiny, tiny, tiny little effect size. It's going to be well within the margin of error of measurement. You know, most of the time you get measured within like a quarter inch. So how many people would you need to measure, you know what I mean, to detect that your drug, like, let's not even call it a drug. Let's say that the drug is putting a very small piece of wood underneath your heel. So you're literally a 32nd of an inch taller, right? Literally the intervention is, we're going to give you platform shoes, but very, very small platform shoes. Did it work? Like, you can't tell unless you have a huge number of people. Does that make sense? So, like, if you give people platform shoes that are like 5 inches tall, yeah, you can measure that real fast. When you have a big effect size, you know, when everyone's coming in 5 inches taller because they're on like these giant platform shoes, yeah, it's easy to tell that it worked. But when you get an answer of no, it didn't work, that doesn't mean it didn't work, right, necessarily. It could just mean you don't have enough data yet. So if you have very, very, very small platform shoes and your margin of error on your measurements like a quarter inch, yeah, you probably could figure out that it worked if you had, like, I don't know, thousands, millions of people. You know, you get enough people in there, and that extra 32nd of an inch might be enough to kick people up to the next quarter inch enough times that you would be able to detect it eventually with enough trials, right? And that's how science is. If you have a small effect size, it's hard to tell if it worked or not. If you have a big effect size, like if every time you gave out the Galaxy drug, people doubled in height, yeah, sure, 5 people's enough. You know what I mean? Does that make sense? It's like the more obvious that it works, the less people you need. Does that make sense? Like you turn into like I don't know, the Hulk or something, you know. Right. So rather than having 100 people, if the average change was 5 inches, no, then it's significant also. You see that? So if we gave the Galaxy pill to 5 people, and on average they gained 5 inches, then with the same standard deviation, the same count, then it's significant. Do you see that? So when there's a giant growth in something, like the stats go, yep, something happened. When there's a small effect size, then you typically need more people to kind of suss out, like, did something happen or not, right? And so our original case here, we only had a change in 1 inch, and the standard deviation is 2 inches. So it's like plus or minus. So we gained 1 inch plus or minus 2 inches, right? And so that was gray enough that we couldn't tell if it was doing something or not. Cool. So your next homework assignment, which will be due next week, and I'll just give you till, I guess, Thursday to do it, is there's going to be 2 parts to it. The first part is you're going to write a program. You're going to write 3 programs, actually. The taller you are, the more likely you are to die young. Man, I hope not. I'm 6'6", dude. So, might be too late for me to die young. I don't know. So the first part of your homework assignment is you're going to write a program that will generate random numbers. Okay? You guys all know how to do that? SRAND, or you can use the C++ random library. Do you guys know how to make random numbers? You remember that from C-Sci 40? Aaron, you here? You remember how to make random numbers? Okay. But they're not going to be just like random. You know what I mean? What I want you to do is SRAN modulus 100. Yes, if you do SRAN modulus 100... No. Not SRAN modulus 100. So let's go over that. So if you're using the C random library, which is fine, nobody cares. There is hashtag include random if you want to go into that. I really don't like the design of the random library, so I don't use it as much as I should because it's better. But I shouldn't, whatever. It's kind of ugly. So sran times 0 sran seeds the random number generator. It does not generate a random number. It initializes the random number generator. Okay? And the current time is in seconds. And so if you run the program again, within the same second, you'll get the same random number. This is not a good system. The C way of doing random numbers is garbage. It's really bad for a lot of reasons, but it's easy to remember. So, I've actually had that conversation with people online in the last couple weeks. Like, we're maybe getting finally a good random number generator in C++ that's not stupid. Like, you'll actually be able to say rand int, give me a random integer from 0 to 99. Like, that's coming. Apparently, it's in the experimental TS. So I'm excited for that, because, like, I hate both options that I have right now. Either option 1 is use C, which is technologically deficient for a number of reasons, like what if I call the program twice in the same second? I'll get the same random numbers. That's not good. And then the random numbers you get are also bad. And so you can do rand modulus 100 plus 1, C out that, and this will print a number from 1 to 100. Okay. So that's option 1. That's one thing. But this is a uniform distribution. So this is a uniform distribution from 1 to 100. All right. What I want you guys to do is, for your next homework assignment, you will make 3 programs that generate random numbers. Okay. One of them can be uniform, but the others should be Gaussian-ish. Okay. So what does that mean? Remember how we talked about rolling 3 dice and adding them together, and it gets kind of bell curvy looking? Something like that. Okay. And I want you to write down and submit on Canvas the following. The name of the program, the mean, average, expected value, standard deviation, how wide the Gaussian is. Okay. And then you will copy it into /temp. Hopefully I don't reboot the system. This temp gets rebooted every time I reboot the system. You'll copy it into temp, and then chmod everybody may read x temp your executable name. So for example, copy a.out into /temp Garcia1. Okay. Then do Garcia2, Garcia3. All right, so Tomas would have 3 executables put up into temp, named Garcia1, Garcia2, Garcia3. Cheryl will have one named Cheryl1, Cheryl2, Cheryl3. Okay, and then you need to make it world readable. then make it world readable and executable like this. So this will make your program executable by everybody. Okay. And I want you guys to all have this done by Thursday. I know that Andrew is due on Thursday. This is also pretty damn easy. Okay. So the only thing you might have a question about is the mean and the standard deviation. So just generate 100 numbers, whatever, out of your random number generator. Like this week Thursday. Yeah. It's literally like, it's like 5 lines of code. Like it's not, this Thursday, 2 days from now. Just make, it's like, this is it, right? Let's have it generate 100 random numbers. Okay. There, this is your first program, or whatever, you know what I mean? Like that's it. Like, that's the whole thing. Yeah. You just make 100 numbers. Okay. And what we're gonna do is you're gonna make 3 random number generators, and don't do this one. Obviously it's a little easy. And then what you're gonna do is for the second half, which we'll talk about on Thursday because we're almost out of time, is other people are gonna pick 3 random number generators out of the temp directory and try to guess these values. Guess the mean, get the standard deviation. So on Thursday, you're going to have to submit to me the name of the program, Garcia1. The mean, it produces a number whose average value is 1,000,000, whatever. And then the standard deviation is 3. So it's going to produce numbers most of the time, 68% of the time, between 1,000,000, 1,000,003, and 999,997. 68% of the time it'll be in that range. And so by a Gaussian or Gaussian-ish, you need to generate like multiple dice rolls, right? Like rolling 3d6. So this is a uniform distribution. One of yours can be uniform, but I want most of them to be roll 3 dice, add them together, good enough. Roll 50 dice, add them together, good enough. Okay? It doesn't matter how many dice you roll. The more dice you roll, the more Gaussian-ish it becomes. And then I want your code to spit out 100 numbers. And then it's going to be the job of other people. This is why it has to be done by Thursday, so you have a week to do it. They're going to guess the mean and the standard deviation of your program. Okay? So let me show you how to do this in option 2. Use the C++ random library 100 numbers. And it's a bit of an unfortunate coincidence we used 100 here. So I'm going to change this to 10 just so that you don't confuse this 100 and that 100, right? They're completely separate. So this will make numbers from 1 to 10. So the C++ random library is unfortunate in that you have to Google it every time. CPU reference random, because it's complicated enough that, like I said, in the experimental TS right now, there is there's just a rand_int function that just gives you a random integer in a range. It's like, yay, finally we've got something good. Instead, we've got this stuff. And if you're looking at MT19937_64 and be like, who thought that was a good idea for a thing? Like you'd be probably accurate and justified in your criticism of the C++ standard library, because this looks terrible. And it really does look terrible. And there's actually an ongoing debate on the standards mailing list right now as to how to properly seed the Mersenne twist engine, which is what the NT stands for. So I got 5 minutes for my meeting, so let's see if I can show you how to make a random number generator real fast. Here, uniform distribution. I know, chill. There, that's how you do it. 2, 3, 4, 5. 1, 2, 3, 4, 5. Done. Okay. So, bloop. Insert. You have to make a random device. You make a Mersenne twister. You don't have to use a Mersenne twister. There's other options. You feed it the random device. You can create a uniform int distribution that'll generate numbers from 1 to 6, it looks like. We'll do 1 to 10. Oops, because that was what we had before. And then 100 times. Switch this into my preferred format. Okay. Followed by. They like their STDs. That. Okay, so this is going to generate a number from 1 to 10. And if you look at all that nonsense, yeah, there's a reason why I dislike it. This is not easy enough. Look at how big that word. Like, it's not easy enough for like a CSI 40 student to memorize. This is, right? Shahab still remembered this from, a year ago. Nobody remembers this unless you do it often enough that it gets engraved in your memory. But this is just poor language design, in my opinion. Okay. So, get rid of our STDs here. And there we go. So compile that. Compile main.cc, run it. And we got numbers now. Okay. So, pick one or the two. You don't have to do both. But let's say... we'll do it 3 times, right? So this is going to generate rolls 3D times. Okay. So this code here is going to, this is Gaussian enough. This is a uniform distribution, right? This is enough Gaussian to be acceptable for this assignment. All right. So, whose idea was the name of that? I know. It's not just me, by the way. I can be fairly critical of, because my lens on this kind of stuff is like, what is easy for you guys to learn? Like, I advocate very highly for having readable and simple standard library stuff so that my students can do it. Whereas most people on the standards committee or on the mailing list, at least, are like, I work as a high frequency trader person for a fintech company. I have different needs than readability, whereas I want things simple and easy. They want fast and low overhead. There's different priorities to things. To Gauss, yeah, just add multiple rows. Yeah, do as many as you want. I would say 3 at a minimum. Could be 5, could be 10. Doesn't matter. And then after, you can do either of these approaches. For this one, you can just do this several times as well. Right. Non-uniform now. Okay. Either of the two. Don't do both. Just do one. Okay. And make 3 of these, put them up on temp. This is an easy assignment. It's an easy pickup of points. Okay. And it's only a 5-point assignment, but still it's 5 points. So I'll throw this up in temp. Copy main.cc up into temp. Chmod everybody may read /temp/main.cc. So there you go. Grab a copy of that, and then by this time in 2 days, I want to see 3 executables from each one of you. Okay. I got a meeting in 1 minute. Nope, meeting's starting now. All right, so that's it. Have fun making that. That should take you no more than 5 minutes, 10 minutes to do. So have at it. All right. Thanks, guys. See you on Thursday. If you have any questions about this, post on the Help Center. All right, peace out.